This is a moments example based on a lamina. So just effectively, for what we're interested in, it's just a 2D shape with no depth effectively. We've got its measurements here, and we've told the center at C. Because it's a uniform lamina, the center is going to be the bisection of the two diagonals, what most people consider the middle, and we've got a weight force of 8 newtons. So I'm just going to draw this a little bit bigger so I can write all over it, or draw all over it. So instead of calling that 0.6 at the top, I'm going to call it here 0.3 meters. I'm going to call this 0.3 meters. So when I put the center on, I'll see the distances from there. Similarly, I'm going to call this 0.2 meters, and I'm going to call this 0.2 meters. By having my own diagram, I've not got to see the 0.4 and 6, but I can obviously understand those are the distances. So when I look at the fact the weight is going to hang down from here, this is how we understand it when we're doing it from a lamina. It's going to be 8 newtons from there. It's going to be like having a little bit of paper on your finger spinning it around effectively. Then I can find, so we've got P is the bit where apparently we're told is going to be the pivot by the looks of it, where we're taking moments from. So, part A. Find the moment about P of the weight force. Okay? Is there another? Oh, there's a 12 Newton force. Oh, I've missed that off. Let me put that on. So there's also a 12 Newton force going that way. Missed that one. As we were. Right, so this force here, the distance, so it's 8 newtons and it is a distance. So if I'm taking this as a pivot, that is the perpendicular distance there that I've marked on. I'll do it a bit thicker. That is the perpendicular distance, as in how far that red arrow is from the dot, going the opposite direction to the way it's going, as in perpendicular. So that's why I put the 0.3 meters on. So I can say that that is 0.3 meters. So we generally do things in meters. So 0.3 distance times by 8, which is going to give me an answer of 2.4 Newton meters. Oh, and obviously I haven't mentioned the direction. So attached there, pulling here, so it's going this way around, which is known as clockwise. Help if I actually put K there. There we go. And then for the 12 Newton force attached here, it's pulling this way, and because it's pivoted at the bottom, it's also going clockwise. This time, the distance is this distance here. So how far from that pivot, perpendicular to the force. So the force is going right, so the distance is a vertical force. The distance is vertical, the force is horizontal. So it's not this distance, it's perpendicular distance, and that is the 0.4. So this time, it's going to be 0.4 meters times by a force of 12, which is going to give me 4.8 Newton meters. And as I said before, pivoted down there, so it's going to pull and then loop round, so it's clockwise as well. So quite often we look at the sum of two forces because they're both acting kind of at the same time, pivot at the same point. So these would give an overall turning force of 7.2 Newton meters, both going clockwise if we were to consider it together, like we will do in a lot of the exam style questions to follow.